In this video, I'll be explaining the dynamics of motion of an elevator or a lift system. I'm sure you must have used one before. And if I want to ask now, tell me your experience. The last time you used a lift, maybe to go from the ground floor, let's say you are getting to the 10th floor or 20th floor of such a story building. And I'm sure you'll be able to, you have so much to tell me about it. We want to model our lifts. This is our model lift. The model lift has, let's say, in it, a weighing instrument, like a scale. And it's possible to have the display section of the scale up here connected to the scale. So that when somebody stands on the scale, the weight of that person is reflected on the lift. Okay, sorry, on the display section. Okay, so if this person weighs, let's say, 500 Newton, of course, that should be displayed here. I can use a digital, because this is when the world has gone digital. I'm trying to draw analog here. If it's a digital system now, if the person has a weight of 500 Newton, of course, it will record it. It will display the digits, 500 Newton, as the weight of this young man here. Okay, let me draw it very well. Okay, that is a young man there standing on the floor of the lift. And this floor, as I said earlier, is more like a scale. It's connected to this scale that has this display section. So that's our model lift. Let's say the mass of this young man is m, which means his weight is acting downwards. And that is given by mass times acceleration due to gravity. That is g. If I take my g as 9.8 or 10 for simplicity, I can use g as 10 throughout this analysis. So the normal reaction acts in this direction. Of course, normal reaction, let's call that R, is always at right angles to the floor, to the plane surface, or to the floor of the lift. That's the normal reaction. And it is such that the reading on this instrument is the same as the normal reaction. Please pay attention, take note of that. The reading on the scale or displayed on the instrument's display section of instruments is equal to the normal reaction. Okay, normal reaction N, or the normal force R rather. Okay, so that is that in this situation. Now let's take the first case, case 1. In case 1, we say that the elevator is either at rest, number 1, is at rest, or the elevator is moving, that's the B part, it's moving up or down, upwards or downwards with a constant speed. The first case is the case of static equilibrium of the lift and the person in the lift. The second case of moving with a constant speed is the case of dynamic equilibrium, or what we call kinetic equilibrium. Now, in this case, the resultant force acting on this individual is equal to 0. Constant speed means the acceleration also is 0. Okay? Now, what's the reading that is displayed on the display section of the scale of this instrument? Okay? Okay, first of all, the resultant force on this individual is given by the reaction, the normal force, minus the weight of the person. Of course, we know that weight is equal to mass times acceleration to gravity. So that gives me F equals R minus mg. I can decide to take this direction. Sometimes it can also be mg minus R, depending on the direction of motion. If the lift were to be moving, the elevator was moving upward, then we'll go with this as the expression for the resultant force. But if the lift were to be moving in a downward direction, we can decide to take this as the expression for the resultant force. In either case, the resultant force is taken or is equal to 0 in both cases. Okay, so in that case, the reading on the instrument is equal to the true weight of the person, because this mg is called the true weight of the person. So whether the lift is at rest or the lift is moving in the upward or down direction with a constant speed, it means the reading displayed on the instrument equals the true weight of the individual. And let's say the mass of the person there, the mass of that boy is 50 kg, it means that its weight or the reading displayed there is 50 times 9.8, or let's use 10, that gives 500 Newton. Okay, so that is the case one, when the elevator is at rest, when the elevator is moving either in the upward or downward direction with a constant speed. Okay, let's see case two. In the second case now, we go to the next page of my board. Of course, this is my whiteboard. I call this case two. For case two, let's say the lift moves upward, okay, with a constant acceleration, with a constant acceleration, okay. Let's say that acceleration A is less than the value of acceleration due to gravity G. Okay, we want to do the analysis again. Of course, this is the motion of the boy in the lift. Okay, this is diagram showing the boy in the lift. Okay, now I'll draw the display section of the lift. Okay, let's say I'm using a digital scale or a digital balance. Okay, we want to find out the reading. And that reading I said earlier is also the normal reaction that is acting upward from the floor of the lift. Now, the lift moves upward, motion direction. I have to draw this diagram, this arrow, to show the direction of motion of the lift. That's the motion direction, okay? Now, the weight of this boy, of course, mg, is acting downward. The normal reaction, which is also the reading on the instrument, acts upward. Now, I can decide that the motion direction should be positive, meaning that the acceleration of the body, A, is also giving a positive sign. Okay, now a normal reaction or normal force, which is the reading of the instrument, is also in the upward direction. That gives R, but this is negative. So the resultant force on this resultant force on the boy, F, will be equal to the normal force minus the weight of the body. That equals mass times acceleration from Newton's second law of motion. Okay, I can consider these two sides of the equation. Now, recall that R is what is displayed by the instrument. Sometimes we'll call it the apparent weight. Of course, we can call it the apparent weight, which is not going to be the true weight of that boy. As this lift moves up, as this lift ascends with a constant acceleration, that reading is called the apparent weight, not the real. The mg remains the real or the actual weight of that boy there, okay? Then ma is defined as the accelerating force. The accelerating force, okay, which is also the difference between the apparent weight and the true weight. And MA is also called the apparent gain or loss. Apparent gain or loss of weight, depending on the direction of motion, loss of weight of the boy. Okay? Okay, so let's write down this equation now in terms of R. So R, which is the normal force, will be equal to MA plus mg, whichever I can write the other one first. Meaning that the normal force is equal to M into A plus G. So if the boy's mass again is 50 kg and the acceleration is 2 meters per second squared in the upward direction, and we take G as 10, meaning that the reading displayed by the instrument is 50 into 2 plus 10, that gives 50 times 12, that gives 600 Newton. Okay, so you can see that the boy's true weight is 500 Newton, given that his mass is 50 kg. But look at it now, just by this lift ascending with an acceleration that is greater than 0, that is 2 meters per second square, for instance, the reading gives something higher. The scale displays or gives a higher reading, 600 Newton. It like this boy has gained some weight. Just like that. He has not even eaten much. He has gained some weight. For someone to gain weight now, must eat and eat and eat and eat. But just by this lift moving up, it has gained an extra weight. So we can call that the apparent gain in weight. Apparent gain in weight of the boy is given as 600 minus 500, which is 100 Newton. If you recall, so if you check again, that this 100 Newton is the same thing as MA, which is the accelerating force. So which means MA is called the apparent gain because in exam condition, the examiner want to ask you, in this case, you say calculate the apparent gain in weight of the boy. It is 100 Newton, which is also calculated using MA 50 times 2 is the same thing as 100 Newton. Okay, so that is the apparent gain in weight. How about when the lift also ascends with a deceleration? Maybe the boy is nearer his final destination. He's getting to the fifth floor, the seventh floor, the 10th floor, and he's very close to it. The lift must decelerate so that he can stop at exactly the seventh floor for the boy to alight from the elevator. So what happens there? In that case, we take A as negative since it is a case of deceleration. And the resultant force here becomes R equals that's the reading on the instrument becomes mg plus m into minus a. So the reading on instrument will reduce. Okay, that is the case where in the upward direction still, where there is deceleration, the lift begins to decelerate, the elevator begins to decelerate, so that they can eventually come to rest for this boy to alight from that lift. Okay, so that's the case two. I guess you are done with this. Let me move to case three. I'm going to go to the next page of my board. This is my board. Bear with me. That's my board. Okay, so I move to case three. Now, very quickly, for this case three, let me draw this line so that I can manage my space very, very well. Now, for case three now, for case three, we are looking at the case where the lift moves downward. The lift moves downward with a constant acceleration. A constant acceleration, A, which is less than G. Okay, now let me just quickly give a picture or draw a picture of the lift system, the elevator system. Here is the boy again standing on the floor of the lift, and this is the display section of his case, the digital display, not analog, because the world today has gone digital. Okay, the weight of the boy acts downward, that's mg. The normal force acts from the floor of the reed of the lift, and that is what is also equal to the reading that is displayed on the display section of the scale of the instrument, of the weighing instrument, which is something called the spring balance or Newton meter. Okay, so this time around, the direction of motion is downward. Okay, now I want to define something. Since that is downward, I can decide to give this positive, meaning that any force that is acting downwards must be given positive. Example, the weight acts downward. No more reaction acts upward. So give that negative. Since the acceleration is also downward, okay, I can give that also positive. So the resultant force on this lift or this individual there is now mg, which is positive, minus the normal force, which is also going to be the reading that is displayed on the instrument. And from Newton's second law is mass times the acceleration. Okay. Now we look at that quickly so that this is my, I'm going to look for the reading. If you make the subject of the equation, the normal force R gives me mg minus ma, okay? So I can factor out my mass, that gives me g minus a. Okay, so if a is 2 meters per second square, that is, it really descends. So the reading on the instrument will be 50, which is the mass of the ball, into 10 minus 2. That gives you 50 times 8. That will give me 400 Newton. So you can see that this boy is going to have a feeling of, my weight has been reduced. I'm feeling some. You can feel your weight. Okay, the normal weight, the actual weight of this boy, his actual weight is 500 Newton. But by means of, because of this lift, by virtue of the motion of this lift, the boy's, the reading on instrument is 400, which means there's a loss of weight. So the apparent loss of weight, we can get that as the difference between 500 and 400. That gives you 100 Newton. That can also be calculated using mass times acceleration, which are also called the accelerating force or decelerating force. That gives you 50 times 2. That gives you 100 Newton. So that's the apparent loss of weight of this boy by virtue of this lift descending with a constant acceleration. About maybe if the boy is close to the last floor, the lift must slow down so that this boy can alight from the lift system, from the elevator. In this case, the deceleration, the lift must decelerate. The lift must accelerate. So from the same equation, R equals mg minus ma, that is this equation. Okay, now I'll take A as negative, that is the acceleration, negative acceleration. So that means that the reading becomes mg minus m into minus A. That gives me R equals mg plus ma. Okay, that gives descends with an acceleration A equal to the value of g. Okay, what happens here? Now, the downward motion is taken as positive. We still take that as positive, okay? And the weight of the body this time around, mg, will be taken as positive. Acceleration is downward, that is taken as positive. But the normal force is upward. We take that as negative. The resultant force, therefore, is mg minus r is equal to ma from Newton's second law of motion. Okay, so that gives me the reading, which is the normal force, is mg minus ma. So now we are looking at a case where the acceleration of the lift is equal to the value of acceleration due to gravity. So making your substitution there, you have mg minus m. I'll replace this with a g. That gives me 0. Normal force. Now, what's the effect of the reading on this scale becoming 0? That is, let me redraw this. It gives a 0 reading. It gives you 0. This situation is called weightlessness in a lift. Now, in this case, the boy no longer feels his weight. He is apparently weightless. So that is what happens when the reading on the instrument is 0. Now, the second case is that the normal force is 0. It means that the feet of the boy has lost contact with the floor of the lift. That is what we mean by the normal force being equal to 0. Now, in the third case, the resultant force on the boy, which is equal to the mass times acceleration of the boy, of the lift, is equal to the weight of the boy. That is to say, when the resultant force, that's to say, when the reading on the lift is equal to 0. The resultant force on the boy is 0. Okay? Now, we can also see it as a case of free fall motion. The boy starts falling freely. It's like something has gone wrong. Okay? So you need to note something here, that the resultant force, the accelerating force on this boy, is not equal to 0. It is simply equal to the weight of the boy. So that is what happens when the normal force, when the reading on the instrument is 0. In the next video, I'm going to solve some practical questions on this motion in a lift, motion of an elevator. All right, thank you very much.